When an engineering firm receives an order from a client, the first challenge is designing a product that meets all of the client's specifications. During this design process, a lot of expensive and time-consuming testing is necessary to make sure a design is successful. Traditionally, engineers could only test for one or two factors at a time, and many test runs were required to learn all of the interactions among the various factors. A statistical concept called full factorial experiment design provides engineers with a method of greatly reducing time and cost by minimizing the number of necessary test runs to just 8. The idea behind full factorial experiment design is that a product or design can be simultaneously tested for 3 factors that each have their own continuous variance states. When constructing a table for the experiment, we represent each of the 3 factors as x sub 1, x sub 2, and x sub 3, and represent their state of variance with either a negative 1 or a positive 1. 3 factors with 2 variance states each comes out to 2 by 2 by 2, or 2 cubed total combinations, which is where our 8 runs comes from. Our table must be assembled in what is referred to as standard form. This means that combinations must follow a specific order, with each run of the experiment representing a unique combination. In the table we see here, the standard order has been followed for our generic variables and their respective states. So what does this look like in a practical application? In the next couple of slides, we'll see an example of a causal relationship between 2 separate motor designs and power consumption for an aircraft cargo lift while accounting for load weight and centering. Full factorial experiment design should help us understand more about how both motors behave under different load stresses, thus pointing us towards the most power-efficient model. In this table, we see that our 3 factors are shown: load weight, load centering, and motor design. Each factor has 2 variance states. Load weight is either low, negative, or high, positive. Centering is either balanced, negative, or off-center, positive. And we have motors type A, negative, and type B, positive. Since this is a real scenario, we have complemented the upper and lower variance bound markers with actual values. We have also doubled the number of test runs, a process called replication, in order to provide a better average value for each response. This table is the same as the one we just generated in the previous slide, except the standard order has been replaced by a random order and 3 center point runs have been added. The reason for randomizing the experiment is to help account for outside variables of influence. If 2 like combinations are run at different times and temperatures, it will eliminate both of these variables. Adding center point runs is a final important aspect of full factorial experiment design because it proves that the relationship between factor and output is linear or not. If the relationship is not linear, then the result will be misleading and a different type of experiment design should be used.